Hello, this is our Management 565 video lecture series on human and other resource allocation. So our plan for our agenda for this series is to introduce linear programming, our decision-making method to allocate human and other resources. Which we will use to work through a simple example two different ways. All the way through in front of you, so to speak, and then to have you practice two different types of problems that fit within this model transportation problems and assignment problems. Linear programming adds something to the mix with respect to decision making. So if you think about, say, an optimistic decision maker or a realistic decision maker, they might look at all the possibilities and decide which ones they think matter and make the best choice given those assumptions. And the linear program looks very similar, but the additional technology, I guess you would say, is an inclusion of constraints in the decision-making process. So so perhaps the best course of action for everyone is to do a certain thing, but we can't all do that. So even though the maximum would have all the employees behaving in one way, we can't let all the employees do the same job. They all have to do different jobs. So who gets to do the coveted job and who gets to do the other jobs? So that's an example of how a constraint can enter in. So as much as if you think about a for-profit hospital, as much as they would love to have every last practicing medical doctor and nurse working in the most lucrative subspecialty, that's not how the universe works. So they can maybe assign more professionals to that area, but you certainly can't assign everyone. So linear programming is a way to maximize an objective or minimize a cost. So the skill of the employees, the cost of the transportation, mileage, profit, subject to constraints on the inputs. So we are going to, as an assignment problem is a great example. Suppose we have 8 employees and 5 jobs that need to be done. Who should we call in to do what job? So why can't we have all 8 people working? Well, we only have 5 jobs, and you can't have more than one person per job in the scenario. And so that would be a natural constraint to place on the optimization of the best person for the best job. Similarly, you can't put the same person in 2 places at once. Like, it's a constraint of the physical system. So we want to put the best people in the best jobs, but subject to the constraint, they can't be in 2 places at once, and we can't double book. So in general, when we think about resource allocation in the linear programming context, there must be some kind of objective that we're maximizing. So if we think about profit, perhaps there's a choice between several different kinds of products we could offer, or different prices we could charge for the same product. Each of those choices is going to have an effect on a lot of things. It'll affect customer goodwill. It will affect hiring and firing of employees. It will affect the long-term viability of the brand. It will affect research and development, and will also affect profit. Um, Linear programming operates under the assumption that you have one objective function that takes all the inputs, everything you're doing, and produces a set of produces a number. And the reason that we have to assume it produces a number is because we're going to maximize that number, or maximize the benefit, which can be maximizing a good thing or minimizing a bad thing. So that's optimization, single dimension optimization in general. We've got some function that takes a bunch of inputs and produces one number as output. So to be a linear program, the method we're going to use to solve problems in our series, the function must be a few things. So first, it has to be constant over time. So the profit you get from selling buggy whips in 1910 needs to be the same as the profit you get today. Certainly that's not true in that case, and often isn't true in general, but over short horizons can be approximately true. The constraints on the problem have to be proportional to the inputs. So for example, we could think about, say, the like a shoes problem. So we would not like to be selling shoes and have an odd number of shoes, because the last shoe doesn't have a mate and will not sell well. And so that's a constraint, that the inputs on shoes need to be even, but that's not one that would fit within the context of linear programming, because the constraints have to be proportional to A. There needs to be some limit on the amount of A, or a direct multiple of A. Another important feature is the benefit of choosing one part of your inputs doesn't depend on another part. So if let's imagine that we could think of a constraint. I can't have more than 2 professionally qualified people teaching in a Masters of Education program. I need to have the rest doctorate qualified, but that's not true if the professionally qualified people have a certain number of peer-reviewed publications over a certain time frame. Well, that's things interacting, right? That would be we need to have, if this happens to occur, then this will occur, which changes the thing. It can't work like that. It has to be it would just have to be a hard cap of 2 that doesn't depend on something else. Another sort of odd quirk of linear programming is, for simplicity, we assume fractional inputs, and that can be strange at times. So if you think about an assignment problem, if we want to have one person in one job, we solve it as if you could put half a person in one job and half a person in a different job. The solution for an assignment problem won't include fractional people, but it can seem strange to have to wander through that to get to the right answer. So in general, though, for a linear program to work, we need to be able to just operate in decimals for all of our inputs, and that can feel strange at times. So let's do an example of a linear program and what that might look like. So suppose I have, I'm thinking about a 13-year-old child who is going to spend an afternoon at an arcade, and she plans on eating pizza and playing her favorite arcade cabinet game, Metal Slug. So naturally, there are a couple constraints on the things she can do with her free time. and money. She's only got so many hours that she's at the arcade, and she only has so much money. And so, and there's a natural trade-off between the two things. If she eats pizza constantly, she will run out of money quickly. If she plays Metal Slug constantly, she'll run out of time quickly. And so there you can imagine pretty quickly that it will not be best for her to focus entirely on an expensive thing or a time-consuming thing. That it might make sense to sort of mix the two, and that way she can spend her money and use all her time and maximize the fun. Now, our objective is to maximize fun or enjoyment of the outing, but again, because this is a linear programming problem, we need to assign a numerical value to the things that she's doing. And so we do that by thinking about a heuristic that pizza for her is, a slice of pizza is about as satisfying or appreciated as 4 games of Metal Slug. So if she had to choose all else equal between pizza and 4 games of Metal Slug, she'd be pretty indifferent. That means, so using that, we can assign a function that awards 2 points for every pizza slice eaten and 0.5 points for every Metal Slug game played. Why not 4 and 1? It doesn't matter. The only thing we're using the utility function for is to discuss the relative importance of these two things. So like a scaling of the function, if you multiply by a constant, the optimum will still be in the same place. So it doesn't really matter. It's the absolute value of this function. It only matters the relative value because we're going to be maximizing it. All right, so we have our objective. All else equal, we get 2 points for a pizza and half point for a game. Pizza slices cost $4 and Metal Slug cost 25 cents. And she has an $8 budget. So right away you can see we're going to be limited to 2 slices of pizza or 32 games of Metal Slug. Moreover, slices take 15 minutes to eat, and Metal Slug takes 10 minutes to play. And she has an hour. So she has a time budget, and she has a monetary budget. So let's do a graphical solution of this problem in Excel here. Alright, so you've got pizza, you've got Metal Slug, and we have the benefit, time, and money. So for each choice, so each value we get for pizza, so for whatever we choose for pizza, let's say we choose 1 slice of pizza, we're going to get 2 times that in utility from our benefit function. We're going to consume 0.25 hours, and we're going to consume $4. Right? If you remember, that is our $4.25, 0.25 hours, and then Metal Slug, it takes 10 minutes, which is 1/6 next. Oh, we're not there yet, but yeah, 15 minutes to eat is 1/4 of an hour. Okay, so Metal Slug is worth 0.5 points. Oh, sorry. So let's say we choose to play one game of Metal Slug, then we will get 0.5 points. And the total time used will be 1/6 of an hour. And the total money spent will be 25 cents. So if she chooses to eat one slice of pizza and play one game of Metal Slug, her total benefit is going to be 2.5. She will spend 0.41 of an hour doing things that she likes and spend $4.25. So you can see right away she's got more money and she has more time. So chances are she will want to be either doing more of one or both of these things. So how do we know what the best thing to do is? Well, that's where there's a couple different methods. So the first method will be to do the corner checking method, and the second method will be to do the Excel solver method. So when we come back, we will do those two solution methods and go from there.